Hello everybody, my name is Gloess from Fraunhofer FEP, and this is the second talk of the optics session of the SBC Virtual Technical Conference. And the title of my talk is Inline Magnetron Sputtering for Highly Demanding Laser-Optical Coatings. So here you see my co-authors, so Andy Thrasher, Ullrich Manuela and Peter Frach from FEP, Martin Ebert from Laser-Optical GmbH and Hagen from Serial Technologies. Here's the content of my talk. I will start with an introduction about our PreSensLine pilot coater for precision optical coatings. And then I will show you two examples. This is an evaluation for laser mirror coatings in our PreSensLine machine and laser optical coatings for the backlight of a holographic 3D display. And I will summarize at the end. So here's our machine. So it's some kind of inline coater with only one load look. So we load the substrate to a substrate carrier, then we move in the carrier into the machine. Then it's coated and it comes back the same way, so we have only one load look. So here are some features of the machine. So it's a machine that is mainly dedicated for precision optical coatings and coatings for sensor applications. The substrate size is up to 650 times 750 millimeters, thickness up to 120 millimeters. We have two coating stations, and when we deposit optical layer systems, one is for the low index material and one is for the high refractive index material. We have an additional plasma source that we need for the silicon oxide process to get a higher layer density. We achieve a low defect density. This is, as you see, it's a vertical inline coater, and substrate movement, so the things that are needed to move the substrate are below the substrate. So there's no particles from some movement system. The movement system is very precise. I will say a few words about this later. We can heat up the substrate up to 400 degrees C, and we have an inline monitoring. Here you see three important process components at our machine. So we use rectangular magnetrons of FEP for the layer deposition. So these are planar magnetrons optimized for reactive layer deposition. So they have racetrack targets and a hidden anode. This is a view at our precision linear drive before it was mounted into the machine. So there's a total length of 6 meters and it's extremely precise. So this is one key to achieve a very high reproducibility of our layer systems. And this is our in situ adjustable trim shield. So we can adjust the layer thickness distribution from coating to coating just by adjusting these small screens, and the width of the screens is 2 centimeters. So these two components here were built or developed by LSR. The adjustable trim shield was developed by LSR together with FEP. Now I come to the first application, the laser mirror coating that was done in our PreSensLine machine. So here we have this cooperation with company Laser-Optical. So the aim was a feasibility. We wanted to do a feasibility studies on the deposition of very large optical laser mirrors by inline magnetron sputtering. So very large. It's a feasibility studies on very large substrates. The actual substrate size was much lower, you see here. So these substrates were mounted on an area 200 times 200 millimeters. The layer deposition was done with our RM800 magnetrons. So here you see the sputter power. So we used silicon oxide at 5 kilowatt Deposition rate was not that high. The priority for us was were the layer properties. Tantalum oxide was, we achieved a quite high deposition rate. Layer homogeneity was plus minus 1% on the test area, which was enough for this test. Here you see the layer system. It's a typical lambda quarter stack, 24 at 29 layers, tantalum oxide and silicon oxide, total layer thickness 3.66 micrometers. The aimed optical function was 99.8% for the unpolarized light at 803 nanometers. Angle of incidence 45 degrees. We met this optical function. We measured actually at 8 degree angle of incidence, so this leads to a redshift, so the maximum here is at a higher wavelengths than the 803 nanometers, but we calculated the reflectivity at the 803 nanometers at this 45 degree to be this number, so higher than what was in the specification. Here's the AFM and mechanical stress measurement. We achieved a low roughness below 1 nanometer and a very low mechanical stress. This was actually considerably lower than that of a IBS or of a reference system that was deposited by IBS. IBS is ion beam sputtering. The ion beam sputtering was done by Laser-Optic. And the stress was only a quarter of this, and this is good for many applications, also for the laser mirror coating. Usually this leads to a better stability of the layer system. Laser-Optic measured a very low absorption, so something like 11 ppm from the annealed layer system. The wavelength shift was very low. Here in this graph you see three different deposition or the result of 3 different layer systems. This is our system, so almost no wavelength shift after the heat treatment. The same is true for the Magnetron sputtered layer system from Laser-Optic. And they also deposited a layer system by electron beam evaporation, and here they observed a quite high shift. And so Magnetron sputtering our system had we could prove a high packing density and low porosity of the system. The particle density was low. So this was evaluated by Laser-Optic, and they could prove that the highest particle diameter are below 10 micrometers. And we met this ISO standard. LIDT measurement was done by a partner. They used femtosecond laser with a very short pulse duration, 37 femtoseconds only. This LIDT measurement with a femtosecond laser usually leads to quite high impact on the samples, on the laser mirrors, and usually to quite low numbers in comparison to picosecond lasers, for example. So the numbers are low anyway using this short pulse duration. For the single shot test, we got this number, 0.46 joule per square centimeter, which is a quite good number. For the 100,000 shots at one spot, we got 0.2 joule per square centimeter. It's not a bad value, still a bit lower than what Laser-Optic observed with the IBS sample, so 0.31 joule per square centimeter. And a bit, you can understand this difference when you see these curves here. So the IBS sample has a very narrow distribution. So this crossing point is actually the value that is the LIDT value for the 100,000 shots. And our sample, with our sample, we observed a quite high scattering of the value. And so this number was lower. But, and we attribute this spreading of the values that still some small particles are in the layer system, and they contribute to this, at some spots, to lower LIDT values. So still, we have to do something to make this better in the future. But the current status is that we observed a low absorption, low haze, low stress, low roughness. Particle density was okay. We could prove the suitability for the femtosecond laser application. And so we have a potential process to deposit mirrors on very large substrate. And here I speak about 1 square meter and even bigger in the future. Now I come to the second application, laser-optical coatings for backlights of holographic 3D displays. Here we have a cooperation with company Serial Technologies GmbH. It's a company from Dresden also. So with their holographic displays, they display something like this, so a computer-generated hologram, so it works. And for their holographic display, they need a highly monochromatic and coherent illumination, and this for all 3 wavelengths. So, and one approach is a bidirectional expansion of a fiber laser to the size of the display, and this is shown here. So they use a fiber laser for the illumination. This is, with the first lens, it's upscaled to the centimeter range, a few centimeters, and this beam is irradiated at a very high angle of incidence to a first glass plate. Here it's entering this glass plate, coming out perpendicular on the other side by a volume grading. And then already here, the beam is upscaled to the size of this first glass plate. And then it's entering the second glass plate, and this has the size of the display. Again, very high angle of incidence, it's coming out perpendicular, and in the end it's scaled up to the size of the display. So it's a quite nice way to scale up or to expand this laser beam, but it has a problem. Irradiation at this very high angle of incidence, so the angle of incidence 87 degrees, means 84% are reflected at each glass surface. And as there is 2 times this upscaling, means 97% of the light is usually reflected. And so what they need is an anti-reflective layer system for this light, and to be precise, an anti-reflective layer system for the S reflectance at 87 degree angle of incidence. And we deposited this in our machine. So here's the optical function. So the RGB laser wavelengths are shown here, and for all 3 we got a nice anti-reflective behavior. So we could prove that the optical performance is in spec all over the substrate surface. The substrate size is shown here, so 250 times 350 millimeters. The coating errors were in the range plus minus 0.5%. So these are errors regarding thickness, homogeneity, reproducibility, and optical properties. Yeah, and with this they build up such demonstrators now, or even they are working on a prototype. So I'm pretty sure that in a few years we can buy holographic 3D displays, and I'm also pretty sure that this is possibly an application where very large, precise optical mirrors, optical filters are needed in the future. So this is a future market for deposition machines. Yeah, I will summarize. Hopefully I could show you that our machine, PreSensLine, is suitable for precise optical layer fabrication on the substrate size. We could prove the feasibility for high power laser mirror coatings. And we could successfully deposit this special anti-reflective layer systems for this holographic 3D displays. And I'm sure that in the future, this will be a future mass market, and maybe our process will be a key to reach this. I want to thank the European Union and the Free State of Saxony for funding, and I thank you for your attention.